All right, hello everybody. It's Tuesday, March 9th, I believe. Um, as you may be aware, there was an internet issue at school. The Wi-Fi was out, so I wasn't able to record anything, much less post it onto YouTube. So I'm at home right now, and I'm going to make your lesson now. If you hear any heavy panting or breathing, that's my golden retriever over here in the corner. His name's Audie, and he's being a very good boy, but he might get a little impatient with me talking and not giving him attention. So if you hear anything like that, that's probably just him. Okay. All right, let's go ahead and get started. So today in class, we started with the third and final section of Unit 12, which is gas stoichiometry. Audie, go lay down. Come on. Go lay down. Yeah, he's already started for attention. Well, remember that stoichiometry is basically conversions, but it's prefaced with gas. So let's see what this is all about. So let me give you an example equation. All right, so we have gaseous hydrogen reacts with gaseous oxygen to yield gaseous water or steam. So whenever you have an equation like this, and every substance is a gas, and temp and pressure are constant, that's going to be a big point right there. These coefficients, 2, there's no coefficient there, which means it's 1. And the 2, not only do they mean moles or particles, but they also mean liters. So before we got to this unit, you would say that there's 2 moles of hydrogen, or you could say there's 2 molecules because hydrogen is a nonmetal. So it's 2 molecules. You would say there's 1 mole of oxygen or 1 molecule of oxygen because oxygen, O2 is a molecule, not a compound. And then we have 2 moles of H2O, which you could also say there's 2 molecules of H2O. So that should be nothing new. We've been doing that since unit 9 or 10. Well, what I'm telling you now is if everything is a gas, and it has to be everything, and there's a constant temperature and pressure, the pressure and the temperature are the same, then those coefficients can also represent liters. So we say there's 2 liters of H2O, 1 liter of oxygen, and 2 liters of H2O. Did I say H2O back here? I meant to say H2, excuse me. So now we can use the unit of measurement for volume, which is liters, as in for the coefficients. So let's say that I have another equation here. Methane gas reacts with oxygen gas to yield carbon dioxide gas and steam. This H2O, but it's a gas, so it's going to be steam or vapor. Because they're all gases, and I'm going to tell you that they are at constant temperature and pressure, that those coefficients can also represent liters. So we have 1 liter of methane, 2 liters of O2, 1 liter of CO2, and 2 liters of H2O. So these coefficients are used just like we did mole ratios. They can also be used as volumetric ratios, and that's what this is. These are called volumetric ratios. It's no different than moles, except you're just doing liters instead of moles. All right? So the ratio would be 1 to 2 to 1 to 2. 1 liter, 2 liters, 1 liter, 2 liters. That's the ratio, 1 to 2 to 1 to 2. All right, so let's do a practice problem. Let's do just like we used to do mole to mole, which are a one-step problem, let's do volume to volume. Okay, give me a moment to write out your problem. Here we go. Okay, so what volume of oxygen gas is needed for the complete combustion of 4 liters of propane gas, C3H8? Assume that pressure and temperature remain constant. So what I've always encouraged you guys to do is identify your known. So if you read the problem, you'll see that your known value is 4 liters of propane gas, C3H8. So 4.00 liters of C3H8. And the unknown value, let's see if they're asking you to find what volume of oxygen gas is needed. So you're trying to find X liters of oxygen. Now, what I didn't include, and you would be given this, is the actual chemical equation. So we have C3H8 reacts with O2 to yield 3 liters or 3 moles, coefficient can be either, plus 4 H2O, and that's a gas too. Okay, so if you notice, gas, 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 and they're all it says, assume they're at constant temp and pressure, you're allowed to use those for those coefficients for liters. Okay, so it looks like you're being asked to convert propane to oxygen. So that looks like it's a 5-to-1 ratio. There's no coefficient in front of propane, so the number is 1. And there is a coefficient in front of oxygen, it's 5, so that's a 5-to-1 ratio. That's going to be your conversion. So start with your known value, 4.00 liters of C3H8, and just convert. So according to the equation, there's 1 liter of C3H8, there's 5 liters of O2, 4 times 5 is 20. We want to stick with sig figs. There's 1, 2, 3 sig figs. So there we go. 20 liters of O2. And that's the answer. That's it. One-step problem. This is a volume-to-volume problem. Okay, so that may seem a bit easy. Let's do a little tougher one. Let's do volume to mass. All right, here we go. Give me a moment to write this down. Okay, so we have a lot of information here. Let's identify your known values. So it looks like we have 5.00 liters of nitrogen gas. That's right here. We have 3.00 atmosphere, so that's right here. We have 298 Kelvin. Looks like that's going to be right here. And your unknown is going to be how much ammonia in grams is produced. So let's write that down. X grams of ammonia. Okay, you're not being asked to find liters, you're being asked to find grams. That's interesting. So let's take this one by one. And what I'm going to make for you guys is the script. Okay, this is going to be the script. Use this to try to find future problems where you have to do volume to mass. Okay, so step one, be sure the equation is balanced. Okay, well, just by looking at this equation, it's not balanced. So if you notice, there's 2 hydrogens on the left, there's 3 hydrogens on the right, so put a 3 coefficient in front of hydrogen, put a 2 coefficient in front of nitrogen, it should balance everything out. So here we go. And I'm going to take a sip of my Gatorade. Okay, so check. All right, number 2. You want to convert liters of known substance, which in this case is nitrogen, to liters of unknown substance, which is NH3. Well, in order to do this, you need the volumetric ratio. Looks like we have 2 moles of nitrogen. Actually, I messed up. I apologize, guys. You're probably yelling at the computer by now. There is no 2 in front of that. Excuse me. So 1 mole of nitrogen, or excuse me, 1 liter is equal to 2 liters of NH3. There you go. So let's do the conversion. Five liters of nitrogen, 1 liter on the bottom, 2 liters on top. These cancel out. And so we have 5 times 2 is 10.0 liters of NH3. Now, if you said, oh, I'm done, I got it converted. You just did the volumetric ratio. If you look at your unknowns, it wants the grams of ammonia. So how in the world are we going to get liters to grams? Well, if you look back at your knowns, you have pressure, you have temperature, you now have volume. You can do number 3, or is it step 3? Yeah, step 3. Use the ideal gas law, which is PV equals nRT. Okay, well, we have pressure. I'm not mistaken, it was 3 atmosphere. We have volume, which is 10.0 liters now. We have the constant, and because we're using atmospheres, we're going to say 0.0821 atm times liters over moles times Kelvin. And then this, we have 298 Kelvin. So you're trying to find moles. And once you have moles, you can convert moles to grams. So you want to rearrange this so that you're solving for moles, which is in. So PV equals in RT. Divide RT on both sides. And so your new equation is PV over RT equals in. So it's going to be 3.00 atmosphere times 10.0 liters over 0.0821 atmospheres times liters over moles times Kelvin times 298 Kelvin. Okay, atmospheres cancels out, liters and liters cancels out, Kelvin and Kelvin cancels out. So your answer is going to be moles. So let's do the math real quick. 3.0 times 10 is going to be 30.0. That's on top. Let me do the calculation real quick. 0.0821 times 298. I have 24.4658. All right, and then let's do the math here. Looks like we get 1.23 moles of NH3. Awesome. All right, so now I have moles. And once you have moles, you're going to be able to convert it to grams. So that gets us to step 4. Use the molar. Actually, let me rephrase this. Identify the molar mass of NH3. You're going to use that molar mass. So refer to the periodic table. Well, if I look at the periodic table, nitrogen is 14.0 grams per mole, and hydrogen is 1.00 grams per mole, but keep in mind, there are 3 of them, so that's 3.00 grams per mole. 14 plus 3 is going to be 17.0 grams per mole for ammonia. All right. Now, let's get to the grand finale, okay? Step 5. Use the molar mass of ammonia to convert 1.23 grams, or excuse me, 1.23 moles to grams. Okay, so 1.23 moles of NH3 1 mole of NH3 is equal to 17 grams of NH3. Moles of NH3 cancel out. Let's do the math here. 1.23 times 17. I have 20.91, which should equal about 20.9 grams of NH3. There you have it. That is a volume to mass problem. Use that as a script. Next class is going to be a worksheet on gas stoichiometry such as this, okay? All right, guys. See you.